Okay, thanks for coming, and I would like to thank the organizers for inviting me. The talk is going to be two parts. In the first part, I'm going to go through the main theory of Euclidean distance matrices, or EDMs. And in the second part, I'm going to present some new results to show the power of these matrices. Okay? So an outline. As I said, two parts. In the first part, I'm going to introduce EDMs. We're going to talk about their characterizations. There are a lot of characterizations and some of their properties. And then we'll spend some time on the two classes of EDMs, spherical ones and non-spherical ones. And the emphasis is going to be on spherical ones because these are the more important ones. Then I'm going to talk about the EDM inverse eigenvalue problem. Unfortunately, we don't have much time to go through the eigenvalues, but this would be a nice result to present. So this is the first part. In the second part, these are new results in the last couple of years. And the main emphasis is on spherical EDMs, where you have configurations on a sphere. Okay? So let's start. So first, what's an EDM? An EDM is a matrix whose entries can be realized as the square Euclidean distances, interpoint distances of a configuration. So matrix M by N matrix D is an EDM if there are points and points in some Euclidean space such that each entry is equal to the square of the Euclidean norm. Okay? Now, the dimension of the affine span of the generating points of the EDM is called the embedding dimension. So for example, if you have 3 points collinear in a plane, if the points are collinear, then the embedding dimension is 1, not 2. Okay? So what happened to this? Okay, so the embedding dimension is the smallest dimension that you can realize these points in. Now, the EDM is spherical if the its generating points lie on a sphere. Okay, so if you have points on a sphere, then the corresponding EDM is going to be called spherical. Otherwise, it's non-spherical. And again, the more important class are the spherical EDMs. Yes? You will see later. Yes?
Distance is on the sphere or in the Euclidean?
Euclidean distances. But the points are on the sphere. But the distance is always Euclidean. OK, in the theory of EDMs, there are 3 very important vectors. These vectors appear everywhere. So most of the results I'm going to present, they're going to involve one of those vectors. OK? So the first vector, which is very important, is the vector E, which is the vector of all ones. Okay, so the vector of all ones, we denote it by E, and this is important. It's going to appear in almost all the formulas and all the results. And as a consequence of that, this matrix V is also going to appear everywhere. The matrix V is a matrix whose columns form an orthonormal basis for the complement of E. Okay, so the complement of E in Rn, we pick an orthonormal basis. That's the matrix V. So you can say it in a different way that V should satisfy V transpose E equals 0, so it's perpendicular to E, and V transpose V is the identity. Okay, so that's why it's orthonormal. This matrix is extremely important. It's going to appear everywhere. Okay. The second vector is vector W, which satisfies dW equal E. Now, for that to be true, E must be in the column space of D, and that's true. We're going to prove that. Okay? Now, as I define W here, W is not unique because you can always add a vector from the null space of D, and that's still going to be a W. But for all the results I'm going to present, it doesn't matter which W you pick. Okay? It's going to be invariant for that. So it doesn't matter which W you pick. For some results, you have to make your mind about W, and for that, the best way to pick W is to take W to be D dagger E. So D dagger is the more Penrose inverse, or the pseudo inverse of D. So that makes W perpendicular to the null space of D, if you want to make, okay? But for the purpose of this talk, it doesn't matter which W you pick. It's going to be okay. So these are the two vectors. The third vector is a vector S, which is not perpendicular to E. So E transpose S equal 1. So you normalize it to 1. And that vector S is going to fix the origin. Because if you have an EDM, the distances are invariant under rigid motions. Okay? So if you want to realize these points, you have to make up an origin, where the origin is. And that origin is determined by vector S. Now, two important choices for S. First, you can pick S to be equal E over N. That equivalent to locating the origin at the centroid of the points. So the points that generate D, if you locate the origin at that centroid, that will, this will give you S equal E over N. And most of the times, this is very useful. So for most of the talk, we're going to use S in this way. Now, later on in the talk, if you are dealing with spherical EDMs, and if you already know the radius of the sphere, so for example, if you have problems on a unit sphere, so you know that the radius of the sphere has to be equal to 1, it's very important and very useful to pick S to be equal to W. That's the same W there. And I'm going to present at the end of the talk a new result on that, which if you make this choice, the proof becomes very simple. If you don't make this choice, I don't know how you can do it. Yes?
So D is any matrix satisfying DW equals E, or?
No, D is an EDM.
This is the distance matrix?
Yes, always D is an EDM.
All right.
Yes, yeah, always D is an EDM.
So why is E in the range of D for EDM?
I'm going to show that. Okay, so that's, yes.
Why do we get I n minus 1? Why is it?
Oh, because V is, this matrix is n by n minus 1. Because it's perpendicular to E. It's a basis for the complement of E, which has dimension n minus 1. Okay, so those are going to be very important. It happens that these are vectors which are naturally arise in this theory. Okay, characterizations. So there are many characterizations. Some of them are very useful, some of them not that useful. Okay, so the basic characterization, and you will see why it's called basic, is given in the 30s, and it says that if you give me a matrix which is real, symmetric, and diagonal equals 0, okay? Remember, those are necessary for any EDM. Then this matrix D is an EDM if and only if D is negative semi-definite on the complement of E. Okay, so D has to be negative semi-definite on the complement of E. Now, you can restate this theorem by taking any S such that E transpose S equal 1. Then you can say that a matrix D, which is real symmetric with 0 diagonal, is EDM if and only if this operator of D is positive semi-definite. So this symbol means that the matrix is positive semi-definite. Okay? Notice that this matrix here, I minus S E transpose, is the projection on the complement of E. Now, for any S, for general S, this projection is not orthogonal. If you want to make up your mind and make it orthogonal, you can do that by picking S as E over N. Okay? But for now, let's keep it in general. Moreover, the embedding dimension of D is given by the rank of this matrix. Okay? So if this matrix is positive semi-definite, you look at its rank, that will give you the embedding dimension of D. Now, this matrix is the gram matrix of the generating points of D. Okay? So the gram matrix is given by this operator. Notice that BS equals 0 because of this matrix here. So BS equals 0. So here we are fixing the origin so that the gram matrix satisfies BS equals 0. Notice that gram matrices are invariant under orthogonal transformations, but they're not invariant under translations. So to fix a particular gram matrix, you have to impose a condition like that. Here, the condition is BS equals 0, comes from this matrix. Now, if you are given a D, and you want to realize D, then you get the gram matrix from this formula. And then to get the points which generates this D, you factorize the gram matrix, because the gram matrix is positive semi-definite. So you can factorize it in this manner. And then the rows of P are the points which generate this distance matrix. Okay? So if you want to find the points which generates D, they are given by the rows of P. And here P is n by R, if R is the rank of D. Okay? So we always work in the embedding dimension. That makes the math a little bit easier. Okay, so the proof is very simple for this, so I'm going to give the proof, okay, because it's very simple. So here, let's define two subspaces of the space of symmetric matrices. The first space is called usually centered matrices. These are the set of all symmetric matrices, so that if you multiply A times S, you get 0. And the second subspace is all symmetric matrices whose diagonal is 0. Okay? Now, then you can define these two operators from these spaces. This is the operator as appears in the theorem. And this is another operator from the other way, which is given by this. Now, this is nothing but the cosine law. Okay? So this is the cosine law, and hence K. They call it K because to remind you of the cosine law. Okay? So these two operators happen to be the inverse of each other with respect to these subspaces. Okay? So these are inverse to each other. Therefore, if you have Dij equals square of the Euclidean distance, you can write that in terms of the gram matrix in this way. And then D is just K applied to the gram matrix. And because of this theorem, then D, which is, has 0 diagonal, is an EDM if and only if T of D is positive semi-definite. So it comes from a gram matrix. So this is the proof for this basic characterization. So why do I say this is basic? It is because it makes problems related to EDMs amenable to semi-definite programming. So all the machinery of semi-definite programming can be used in tackling these problems. So this is really useful. Okay? This is quite useful because I have all the machinery of semi-definite programming at our disposal to attack these problems. Okay? Now, it turns out, and you will see later in the talk, that gram matrices are not that useful. It would be better and more natural to use projected gram matrices. Now, in the literature, gram matrices are everywhere. Everybody uses gram matrices. However, not many people use projected gram matrices, and I'll try to convince you that this is really more useful to use projected gram matrices for computational reasons and also for theoretical reasons. There are many instances where the projected gram matrices are more useful and they give better results than just gram matrices. Okay? So what are these projected gram matrices? So here, again, we fix S to be E over N. So I am locating the origin, I'm taking the origin at the centroid of the points. Okay? Again, most of the times, this is what we're going to do. And then, in that case, this operator, this matrix becomes the orthogonal projection on the complement of E. Okay? And then the gram matrix is given by this formula. So you can see here the formula becomes very simple. And as a result of this, then BE equals 0. That's another statement of saying that the origin is at the centroid of these points. Okay? And then this operator, the orthogonal projection on the complement of E is given by V transpose, because V is orthonormal. The columns are orthonormal. So you get this is J, and this is again the definition of V. Now, if you have F, which is the set of all positive semi-definite matrices satisfying BE equals 0, this is a face of the PSD cone. So this is a face, F is a face of the positive semi-definite cone. And it's well known that every face of the positive semi-definite cone is isomorphic to a PSD cone of lower dimension. So in this case, F can be written in this way, which is isomorphic to the PSD cone of order n minus 1. So remember, all our matrices or our distance matrices are m by n, but here you go to n minus 1. So therefore, I can define this matrix X to be V transpose B V. So B is the gram matrix. I sandwich that between V transpose and V. Notice that X is of order n minus 1. Okay? And this is what we call the projected gram matrix. Okay? And the same information is carried by either B or X. So X is positive semi-definite and of rank R if and only if B is positive semi-definite of rank R. Okay? So instead of dealing with B, I'm going to deal with X. And you can always go back and forth. So if you have B, you can get X this way. If you have X, you can get B this way. Okay, so in this way, you can move from the operators K and V to operators K sub V and T sub V in this way. And as a result, the set of EDM matrices of order n is the image of the PSD cone of order n minus 1 under this operator K sub V of X. As a result of that, we know that the set of EDMs is a cone. It's closed. It's convex. Moreover, most of the structure of this cone is inherited from the cone of PSDs. So many of the characterization of the faces of the PSD cone carries over to the EDM cone. And again, the basic theorem can be stated in this way. So D, which is real symmetric with zero diagonal, is EDM if and only if this matrix here, which is the projected gram matrix, is positive semi-definite. Okay, so now you are dealing with n minus 1 by n minus 1 matrix. Okay, and the embedding dimension is given by the rank of D. So X does the same job as B, as the gram matrix. Now, V is very useful if you do theoretical, for theoretical purposes. If you are trying to prove theorems, V is very nice and very convenient. However, if you want to do pencil and paper calculations, computations for small EDMs, okay, that's not very useful to use V. Instead, you use this matrix U. Notice that U is very sparse, okay? And still, the columns of U form a basis of the complement of E. However, this basis is not orthonormal. So you lose the orthonormality by doing this. But then this becomes really convenient for computations by hand, if you do computations by hand. And the theorem, so the basic theorem can be stated as such. If you have D, you factorize D in this way. And so this is the first row. This is the first column. Then if the diagonal is 0, then this D is EDM if and only if this matrix is positive semi-definite. That's very convenient for numerical calculation, especially done by hand. It's really useful.
Sorry, what is E index n minus 1?
This means the vector of all ones in dimension n minus 1.
Okay.
Because the E by itself is in dimension n. So to remind you that it's n minus 1, we put E minus 1.
T would be n minus 1 times n.
Yes. Yeah, it will be n minus 1 by n, yes. I wrote it T transpose just for space. I don't want to lose too much space. Okay? Now, it happens that this choice, if you take this matrix U, this is equivalent to setting S, remember our friend S as the first standard unit vector. So the first standard unit vector is the vector where you have 1. The first component is 1, and then everything else is zeros. Okay? Or, to put it another way, it's if you set the origin at the first point. Remember, you have the freedom to set the origin. If you set the origin at the first point, then you get this formula. So again, this is very useful for pencil and paper calculations. Okay, here's a new result. So that, what I said so far is very well known and old. This is a new result, which is how to characterize 0-1 EDMs. Okay, so if you have a 0, 1 matrix, how do I know it's EDM? Now, if you have 0, 1 matrix, then that's adjacency matrix of some vector. Okay? So which vectors will have their adjacency matrices EDMs? And this is a very, very nice thing for vectors. So if A is the adjacency matrix of a simple graph, then A is an EDM, if and only if G is a complete multipartite graph. So this is generalization of complete bipartite graph. This you have multipartite graph. Okay? There are many. Another way to define this is to be the complement of a cluster graph. So what's a cluster graph? A cluster graph is the disjoint union of cliques. Okay, so cluster graph is the disjoint union of cliques. If you take their complement is a complete multipartite graph. And the result here is if and only if. In one direction, the proof is not that difficult. In the other direction, it's more involved. You have to do more work.
So
yes?
the adjacency matrix is 0, 1?
Yes.
Okay.
Yeah, adjacency matrix of a graph is a matrix which has 0, 1. And because the graph is simple, there are no loops, so all the diagonal is 0. Okay. Okay, EDM completion. So this problem has received a lot of attention recently, especially matrix completions in general. So I'm going to say a little bit about it. So if you have a matrix A, it's symmetric partial matrix. So some of the entries of A are given and some are not given. Okay? And it's symmetric in terms of the specified or given entries. So the question here is, how do you choose the unspecified entries? So the entries which are not specified, you want to choose them in such a way that the resulting matrix is EDM. Now, you can solve this problem in two ways. The first way is by noting that the specified entries of A define a graph, okay, in the natural way. So the specified entries, the given entries, define a graph. Let H be the adjacency of this graph. Then you can formulate this problem as this semi-definite program. Okay, this is a semi-definite program for that. Now, because the objective function is 0, any feasible solution is an optimal solution. So if you don't care about, if you have many ways to complete the matrix and you don't care about which one to pick, you can take this way. Now, notice that this is given in terms of the projected gram matrix. Again, X, not B. Projected gram matrix. Now, there is an upside and downside of this formulation. The upside is that if you know a way, usually for most practical applications, you need a solution X which has low rank. Okay, that's a big problem. If you know a way to do that, then you can put that in the objective, on the objective function. So that's the upside. The downside is that here may not satisfy Slater condition. So you might lose Slater conditions, and then you have to do facial reduction. Another way to do it is to formulate it in this way. This way, you can put all the complexity in the objective function, and then the constraints are very simple. So the constraints are just saying that you have to be in the positive semi-definite cone, and all the complexity is in the objective function. For this formulation, obviously, Slater condition holds, and you can prove that for the dual, Slater condition holds if the graph is connected, which is usually the case. Okay, so this is another way to do that. Okay. Also, this solves another problem. If you are looking for the closest matrix to a given, the closest EDM to a given matrix, you can also formulate it in this way. Okay, so that's what I call the basic characterization or the fundamental characterization. There are other characterizations. This is another characterization which says that D real symmetric with 0 diagonal. Notice always we assume that. In all characterization, this is assumed. Then we assume that D has exactly one positive eigenvalue. Then D is an EDM if and only if there exists a W such that dW equal E, and E transpose W is greater than or equal to 0. Okay? That's very useful also, characterization. Now, whether E transpose W equals 0, or transpose W is strictly positive, has geometrical significance, which I'm going to explain later. Okay? So there is geometrical significance attached to these two conditions. Okay, now for Cayley-Menger matrices. So in the 30s and 40s, when people dealt with the distance matrices, usually they dealt with Cayley-Menger matrices. Okay? So what's the Cayley-Menger matrices? If you have an EDM, D, then you can add a row this way and a row this way and a column this way. Remember, E is all ones. Okay? So all the vector of all ones. This matrix M is a Cayley-Menger matrix. Notice that M is n plus 1 by n plus 1. So it's one order more than D. Okay? Here's another characterization of EDMs in terms of Cayley-Menger matrix. So D, again, real symmetric, zero diagonal, is EDM if and only if the Cayley-Menger matrix has exactly one positive eigenvalue. Okay? So the result here is if and only if the Cayley-Menger matrix has one positive eigenvalue, in which case the rank of M is equal R plus 2. R is the embedding dimension of D. Okay? So this is a third characterization of EDMs. Now, recently, I got these two results to push this further. So here, D is spherical of radius rho less than or equal to 1 if and only if M is an EDM. Notice that here it only has one positive eigenvalue. Here you want M to be EDM. So if M is an EDM, then D is spherical of radius less than or equal to 1. And a special case, D is spherical of radius 1 if and only if M is a non-spherical EDM. So notice that as you go down, you increase more condition. You put more condition on M. Okay? Now, there is another characterization yet.
I'm sorry.
Yes?
Maybe it's not a question. What about the radius greater than 1? Is it obtained by scaling or is there no story?
No, that creates problems. We're going to touch that. Okay? We're not going to touch that. Yeah. Yes, because EDMs can be both spherical and non-spherical. If they are non-spherical, then you get 1. Okay? So you're imposing more conditions on them. Okay. So here there is another characterization in terms of the leading principal minors of Cayley-Menger matrix. It's very complicated, so I'm not going to give it. And for many papers in the literature before, like the 50s and 60s, that's what usually people will use. Okay? And there is also another use for Cayley-Menger matrix, which is really useful. So here, if you have points which are affinely independent, so they form a simplex, and if V is the volume of that simplex, then the square of this volume is given by this expression in terms of the determinant of the Cayley-Menger matrix. Okay? So the determinant of the Cayley-Menger matrix gives you information about the volume of the points that generates D. Notice that here, this is equal to this expression in terms of the determinant of the projected gram matrix. That's why I said somehow the projected gram matrix has more significance than the gram matrix in this regard. Okay? And you can see here that if the points are affinely independent, so they form a simplex, then the determinant of D is not equal to 0. Okay? Here you have to do more work to show that. Okay, now enough with that. Now, Gale Transform. Gale Transform appears in the theory of polytopes. It's a very useful technique in the theory of polytopes in the 50s. Also, it appears in different branches of math. Okay? And for some reason, which is really a surprise, it plays a fundamental role in this theory. And you will see later. Okay? So what's Gale Transform? First, if D is an EDM, and this is the set of all the points that generates the configuration matrix of D, or the gram matrix, if I take the null of this matrix, remember E is the matrix of all ones, That null space, we call it the Gale space. Now, if you pick any basis of this space and form a matrix Z, then Z is a Gale matrix. Okay? Z is a Gale matrix. Notice that Z is n by n minus r minus 1. So it's very important to remember this number here. Now, if you take from this definition, it's obvious that the columns of Z encode the affine dependency of these points. As a result of that, when you are talking about points in general position, like no 3 points on a line, Gale transform or Gale matrix becomes very useful to have. It's really very useful, especially in the theory of rigidity of frameworks. Okay? So this comes from the fact that the columns of Z encode the affine dependency of these points. Now, to get Gale transform, all you have to do is take the rows of this matrix Z. Okay? So the first row of Z is the Gale is a Gale transform of P1, and the second is a Gale transform of P2. The reason I say it's a Gale because Z is not, of course, is not unique. Okay? You can pick any basis, so it's not unique. Okay, now we can discuss the properties of EDMs. So what's the properties of EDMs? The first property is that an EDM has exactly one positive eigenvalue. Okay, it has exactly one positive eigenvalue, and that's not difficult to see because it's negative semi-definite on the complement of E means it has at most one positive eigenvalue. Because the diagonal is 0, it must have at least one positive eigenvalue. So it must have one positive eigenvalue. Also, the null space of D is always a subset of the Gale space. And that's a key step in proving the results that gonna follow. Okay, it simplifies a lot the proofs. So here's what Henry asked before. So E, the vector of all ones, is always in the column space of D. So such W always exists. Okay? So E is in the column space of D. This W always exists. And if D is an EDM, it implies that E transpose W is greater than or equal to 0. Again, this is really useful for later. Moreover, the rank of D is always either R plus 1 or R plus 2, independent of N. So if you have 1,000 points, so if you have, let's say, a sensor network consisting of 1,000 sensors, then you know the rank of this matrix is at most 5, because R is the embedding dimension. Okay? So it's either this or that. Only 2 possibilities for the rank.
So you're implying that the sensors live in R3? No?
Yes, yes, yes. If they are living in R3, the rank of D cannot be bigger than 5. It's either 4 or 5. And later you know which case is which. Okay?
So can I point out that this probably means that D is a squared Euclidean distance matrix?
Always. Always square. Always. Okay. So let's concentrate on spherical EDMs. So spherical EDMs, they have a very rich structure, mathematical structure, and there are many, many characterizations. So you can pick which characterization is suitable for whatever situation you have. Okay. So the first result. Let's take the first result. So if the embedding dimension is equal to n minus 1, this means that the points are affinely independent. Then D is spherical. Okay, D is spherical. So if the points are affinely independent, D is spherical, always spherical. Now, if the embedding dimension is less than or equal to n minus 2, then the following are equivalent. So D is spherical if and only if the null space of D is the same as the Gale space. Okay, so the Gale space is the same as the null space if and only if D is spherical. Again, means the points lie on a hypersphere. Okay. If and only if the rank is R plus 1. Okay, so R plus 1. If the rank is R plus 1, all the points lie on a sphere. Okay. If and only if there exists a scalar beta such that beta E transpose, so this is a matrix to have all the components equal to B, all the entries equal to B, minus D is positive semi-definite. Moreover, the smallest such beta you can find is equal to 2 times the radius of the sphere square. Okay? Later on, you will see some connection with some work in the quadratic assignment problem. Okay? Again, if and only if E transpose W is positive, in which case the radius square is equal to 1 over 2 E transpose W. Okay? And this is very useful if you want to determine or study the radius, how the radius of these points vary. Okay? This is that. If and only if, notice how many. If and only if this system has a solution A. So P is the matrix, the configuration matrix. And in this case, A is the center of the sphere, and this is the radius of the sphere. Okay? These are some of the characterization of spherical EDMs. There are others, but these are the more important ones. Okay? So notice they are very different, and each one is really useful in some cases. Depends on what case you have. Okay, what's the geometry of EDMs? Again, most of the properties, geometrical properties, are inherited from the properties of the positive semi-definite matrices. So in particular, the set of spherical EDMs is convex. Okay, so the set of spherical EDMs is convex. It's very easy to prove from one of those characterizations. Also, the EDM cone, so all the EDM matrices, is the closure of spherical EDMs. Means every non-spherical EDM is the limit of a sequence of spherical EDMs. Okay? So every non-spherical EDM is the limit of a sequence of spherical EDMs. That's why I said sphericals are really important ones. Also, the interior of the EDM cone is made up of spherical EDMs. So all the interior of the cone, EDM cone, is made up of spherical EDMs. On the boundary, you have both spherical and non-spherical. Yes?
And in this case, the set of spherical EDMs is not restricted to having radius less than or equal to 1.
No. That's why, yeah.
Problematic.
Yes. Okay. So this class of spherical EDMs is very, very important. Some of the subclasses or examples of spherical EDMs might be a surprise. They're not obvious that they are EDMs to begin with, much less they are spherical. Some of them are obvious, some of them are not. So I'm going to present 6 subclasses of spherical EDMs. The first class is regular EDMs. So an EDM is regular if the center of the sphere is at the centroid. So the centroid and the center of the sphere coincide. Okay? These are called regular EDMs. And they are characterized as the EDMs which have E, the vector of all ones, as an eigenvector. So E is the Perron vector for D. Now, notice that many of the results for regular EDMs mirror the results for adjacency matrices for regular graphs. Many of the results translate. Okay? And this is an example where they translate. So in the theory of regular graphs, there is something called Hoffman polynomial, and it translates exactly to EDMs. So here, if we have an EDM, let these be the distinct eigenvalues. Remember, it has exactly one positive eigenvalue, and all the others are positive or non-positive. So if these are the distinct eigenvalues, then there exists a polynomial equal to E transpose. So E transpose is the matrix of all ones. Okay? If and only if D is regular, in which case this is the polynomial. Okay? This is the polynomial. So this is exactly Hoffman polynomial applying to EDMs. So most of the results here, you can see there is a lot of connection between regular EDMs and regular graphs. And this is connected to the notion of strength of EDMs introduced by Neumayer. he introduced this notion. So EDMs of strength 1 are the regular ones, and then you go to strength 2. This is related to that. I'm not going to get into that. That gets a little bit hairy. Okay, so that's the first class. This is the second class of matrices. When you have a topology looking like a hub and spoke or star topology. So if you have this topology and then the distance between I and j is equal to Ci plus Cj. So for such matrix, we call them cell matrices, means every off-diagonal entry of the matrix is equal to Ci plus Cj for some non-negative vector C. Okay? So these are called cell matrices. Okay? So these are really useful for hub and spoke topology. Okay? So the distance is going from I to j is Ci plus Cj. Now, it turns out that these matrices are spherical EDMs. Okay? So these matrices are spherical EDMs. Moreover, we know their embedding dimension. So the embedding dimension depends on the number of zeros in C. Okay? So the embedding dimension depends on the number of zeros in C. Okay, here is third class of spherical EDMs, Manhattan distance matrices on grids. Okay? So here, if you have a rectangular grid of unit squares, so you have m rows and columns, and then you measure the distance between ij and kl to be the Manhattan distance, given in this manner. So this D, the matrix D, is going to be nm by nm. Okay, so if it's of order n times m. Then it can be shown that this matrix D is equal to this, where this denotes the chronicle product, and Gn and Gm are rectangular grids of one row or one column. Okay, so if you can write D in this manner, and then you can prove that D is spherical, and this is the radius. Okay, so it's spherical, and this is the radius. Now, these matrices appear in the quadratic assignment problem library. There is a talk today, I think, about quadratic assignment problem. So in the library, there are a bunch of examples. I think they are called Nugent, under Nugent, and these are known of being difficult to solve. These are exactly Manhattan distance matrices on grids. Now, in 2010, Mittelman and Peng were studying this class of problems for the QAP, for the quadratic assignment problem, and they needed a way to decompose the matrix, these matrices, into positive semi-definite matrices because that was useful for them. And then they obtained this result, that n plus m minus 2 half E transpose minus D is positive semi-definite. Notice that this is just half the radius squared, or twice the radius squared. So that follows from the characterization of spherical matrices. Maybe by exploiting the fact that these are spherical EDMs, these results can be enhanced and can pushed further. But for them, they were not aware that these are EDMs. Okay, this example of Hamming distance matrices on the hypercube is pretty much easy to guess that these are spherical EDMs. So the hypercube is the convex hull of all points which are 0, 1. Okay? So in dimension R, you have a vector of R components, and the components are either 0 or 1. And you take the distance as the Hamming distance. And you can prove that D is regular, and the embedding dimension is R, and the radius is given by this expression. Okay? Also, you have this. Obviously, the determinant of D is going to be 0. But if you pick a sub-matrix induced by a finely independent points, so you have a simplex, they form a simplex, then the determinant is given by this. So you can find the determinant explicitly. This is, again, another example. If you have a tree, you can create a matrix of distances between the nodes of this tree. Now, remember, in a tree, every 2 nodes have a unique path. So if you count how many edges on that path, that's the distance. Okay? Then you have this remarkable result, which says that this D has exactly 1 positive and n-1 negative eigenvalues, and the determinant is independent of the structure of the tree. It only depends on n. This is really surprising and remarkable, that the determinant of D does not depend on the tree. It's independent of the structure of the tree. It only depends on n. These matrices arise in telecommunication. This paper was published in Bell Labs journal. So for switching, for telephone switching. And there is a nice result here relating the inverse of D to the Laplacian of the tree in this way. And this vector deg is the vector consisting of all the degrees of the tree. Okay? This is related to other results that I don't have time to go through. Now, it's known, well known, that D is spherical EDM, and this is the radius for these matrices. Okay? This is the radius. This class of matrices is a special case of the class that I'm going to present next. So these are resistance distance matrices of electrical networks. This problem received a lot of attention in the last 10 years. There is a lot of work in computer science on these matrices. So in this case, we have a graph. And so this is the graph. Let's think of each edge as a resistance of 1 ohm. So this is physics, physics 101. Okay, so think of each edge as a resistance of 1 ohm, 1 unit. And then we pick 2 nodes, and then we attach the terminals of a battery. And then we ask, what's the effective resistance between S and T? Okay, so if we do that for every S and T, we create a matrix of resistance, effective resistance. Now, obviously, from physics 101, if 2 resistors are in series, you add them, right? So if the graph is series parallel graph, you can keep doing it, and then you get the effective resistance. But if it is not, then it's not easy to do that. So it turns out that the matrix of all effective resistances is given by this formula. So the more Penrose inverse of the Laplacian of the graph acts as the Gram matrix for this matrix. Okay? So obviously the Gram matrix here and its more Penrose inverse are positive semi-definite. So these are the Gram matrix, and then if you take the operator K, you get a distance matrix, and then that gives you all the effective resistances of this graph. Now, from this, it's obvious that this matrix omega is EDM, and since its embedding dimension is n-1, it's spherical. Okay? So these are 6 classes of spherical EDMs. Now, non-spherical is everything else. Okay? So how do you characterize non-spherical? Of course, they follow from the characterizations of the spherical EDMs. So D is non-spherical if and only if dz is not equal to 0. So Gale, remember Z is the Gale matrix. And the rank here is R plus 2, because R plus 1 goes for spherical, so R plus 2 goes for non-spherical. And then E transpose W is equal to 0, right? Which makes sense because the radius is inversely proportional to E transpose W, okay? Okay, now finally, this is the EDM inverse eigenvalue problem. So if you have given scalars satisfying these inequalities, so one of them is positive and the others are non-positive, and they add up to 0. The question is, does there exist an EDM having these as eigenvalues? Okay. Now, you want the sum to be equal to 0 because the trace is 0, because the diagonal is 0. Okay. This problem is mainly open. There is some work but it's mainly open. It has a very elegant solution for any dimension n where you have a Hadamard matrix for that dimension. Okay? So what's a Hadamard matrix? A Hadamard matrix is a 1 minus 1 matrix. So all the entries are 1 minus 1 and satisfies this. So all the columns are orthogonal. Okay? So all the columns are orthogonal. So for any dimension n where Hn exists, we have a solution for this problem. And this is the theorem for that. So given these lambdas, you form a diagonal matrix consisting of these lambdas, and then you take your Hadamard matrix, and you put the vector of all ones in the first column, and then you divide by, you take H lambda H transpose, you divide by n, you get a regular EDM. Okay? So for this case, there is a solution. For other cases, there are partial solutions, but still, it's mainly open problem. Okay, so that's the well-known open conjecture about Hadamard matrices is that Hn exists for all n which are a multiple of 4. And the smallest n where this thing is in doubt is n equals 668. Okay, so all n less than that, we know they exist. So this is an open conjecture. Okay, so that ends the first part of my talk. Now I'm going to present some new results to show the power of this theory. Okay, so here's the first problem. Suppose I have an EDM. I keep all the entries fixed except for one entry. Let's call it the k-lth entry. Okay, so I fix all entries except the k-lth entry, and then I ask, how far can you perturb that entry and still be an EDM? Okay, so for this, we define this matrix E. E is all zeros except ones in the k-lth and lth k position. And then we let these two numbers to be such that D plus T E is EDM if and only if that number varies in this range. So this is a lower bound, this is an upper bound. Okay, so this means that you're only varying the k-lth entry. You're not varying anything else. Everything is fixed except this entry. Now, this interval is called the yielding interval. Okay, yielding interval. If this yielding interval, if this upper bound and lower bound equal to 0, so you have only that interval consists of 0, then the entry is unyielding. So any perturbation of that entry, the resulting matrix is not going to be an EDM. Otherwise, if it's a finite, then we say that entry is yielding. Okay, here's a characterization of these entries. First, we say that two vectors are parallel if there exists a non-zero C such that x equals C, y. So if x and y are both 0, they are parallel by definition. Okay, here's the first result. If D is an EDM and the embedding dimension is Rn minus 1, so all the generating points are affinely independent, then every entry is yielding. So you can vary every entry and still be an EDM if the embedding dimension is n minus 1. Otherwise, if the embedding dimension is less than n minus 2, then you can define Gale transforms of these points. Then the entry is yielding if the corresponding Gale transforms are parallel. So this is why it's surprising that Gale transform appears here. Okay, so you can find all Gale transforms, and then you can tell which entries are yielding, which entries are non-yielding. Now, this can be done by the theory of universal rigidity, but that would be an overkill. Okay, that would be an overkill. And if the points are in general position, means every r plus one of them are affinely independent, then if the embedding dimension is equal to n minus 2 and the matrix is in general position, then every entry is yielding. Now, if the entry is yielding, you want to know the yielding interval, and there are closed form solutions for that. Okay, there are closed form solutions for that. And notice here there is some duality happening. So if B is the gram matrix satisfying this, if I factorize the gram matrix, I get PP transpose. The points are the rows of P. If I take the more per rows inverse, it's given by this. And if I factorize the more Penrose inverse of the gram matrix, I get this matrix S, and I look at the rows of S. Okay, I look at the rows of S, and then I define these two quantities in terms of this vector S. Then we have this result that if R equal n minus 1, then and if the entry is yielding, and if the embedding dimension is n minus 1, or if the corresponding Gale transforms are 0, then the yielding interval is given by this formula. So this is a closed form solution. Of course, you can solve this using semi-definite programming, but here is a closed form solution for that, and it's given in terms of this S. Now, if you want to find this explicitly, you don't need to factorize B dagger. All you have to do, look at the entries of B dagger. This covers the second case. So if you have this C of proportionality between the vectors, so define this quantity, and then we have this result. So if the embedding dimension is less than or equal to n minus 2, and if the Gale transform satisfy this for C which is not equal to 0, then the yielding interval is given by this formula. Okay, depends if C is positive or C is negative. Okay, here's an example. So take this matrix. So this matrix is EDM. It's generated by these 4 points. It's spherical. Okay, it lies on a sphere, and the radius is 1, and it's regular because the centroid of these points is exactly the same as the center of this sphere. So for this matrix, Gale transform, these are the Gale transforms, and this is the vector W. Okay, you can see this is the vector W because if you add every row, you get 8. Okay, you get 8. So the yielding interval of 1, 3 is theta minus 4 to 0. Okay, so you can change it from minus 4 to 0. Means it's gonna, the distance is gonna reduce. So this entry here, this entry 4 can decrease all the way to 0. Can decrease by minus 4. It cannot increase. It can decrease to 0. Okay. Now, why is that? Look, if you think of this as 3-dimensional sphere, it's easy to show that, to see that P3 can be moved along that sphere all the way till it hits P1 without changing the other distances. And by doing so, the configuration is still spherical. So that's later, important for later on. Okay? So for 1, 3, this is obvious from this graph. Now, can you think for the entry P12 here, for this distance P12, what would be the interval? How far can you change it without losing the EDM? Anybody wants to take a guess? Okay, here is the yielding interval for D12. Here, the distance can increase, not decrease. It can increase all the way to 8, by 8. So this entry can vary from 2 to 10. Okay, and still you will have an EDM. So this, if you vary this from 2 to 10, still you'll have an EDM. Now I think I should skip this. Okay, so this is the last problem to discuss. It's about 2 distance sets. So if you have a configuration of points, and if the interpoint distances assume only 2 values, so you only allowed 2 values for the distances, then we say we have a 2 distance set. And usually these 2 values are called alpha and beta, and we take beta to be bigger than alpha. Here's a question. For any graph which is not complete or null. And you'll see in a minute why. You cannot take a complete graph. So for any graph which is not complete or null, does there exist a configuration of points on unit sphere? So you need the points to be on a unit sphere such that the square distance, Euclidean distance, between any two adjacent points given by this graph, the distance is equal to 2. So all points corresponding to, all distances corresponding to the edges of this graph must have distance 2. And all other distances must be beta, which is bigger than 2. Okay? So this is a spherical 2 distance set. Okay? Now, what's the significance of 2? If the radius of the sphere is 1 and the distance is 2, means every node of the graph is represented by a vector on the unit sphere which are orthogonal. So the angle is 90 degrees, and here means the angle is more than 90. But all of them have to be the same. They have to be the same. This is a simplified version of the problem of orthogonal representation of graphs, which are very important for Shannon capacity and things like that. The only difference is that there you want all the distances corresponding to edges in the graph to be equal to 2, but you don't care about the others. They can have any value, and that makes the problem extremely difficult. Here, the problem is not that difficult because I require all non-adjacent nodes to have distance beta, which is bigger than 2. And another question, a follow-up question to this question is that can two different graphs have the same beta? So basically, they have the same distances, except the configuration is different given by the graphs. Now, last year, Musin proved that the answer to question 1 is yes. So for any graph which is not complete, you can always do that. And the configuration is unique up to a rigid motion. Okay? The configuration is unique up to a rigid motion. However, his proof is not constructive and really involved, and you cannot, it's not transparent. So you cannot answer this second question because you don't know how to get beta or anything about beta. Using EDMs provide a very simple answer to both questions. So in EDM notation, if A is the adjacency matrix of the graph, A bar is the adjacency matrix of the complementing graph, then question 1 is nothing but, sorry. So question 1 is nothing but the question, does there exist a unit spherical EDM? Unit, so radius 1, spherical EDM, such that D is equal to this. So these are all the entries corresponding to the edges of the graph equal to 2, and all the edges, all the distances corresponding to the entries corresponding to non-edges is given by bigger than 2 because delta is positive. Okay? So this is the question, boils down to this. Does there exist such thing? And how do you get it? How do you get delta? How do you determine delta? Okay, here's the theorem. So if lambda 1 is the largest eigenvalue of A bar, so A bar is the adjacency matrix of the complement. So you're talking about the complement. Then let delta, so delta is equal to 1 over that. So delta, this delta is equal to 1 over lambda 1 of A bar. Now, as a result, you can answer question 2 easily. So two graphs have the same beta if and only if the largest eigenvalue of the adjacency matrix of the complement graph are the same. So for example, we can create, if you take the cycles, take the complement of the cycles, all of them have lambda 1 equal 2. So beta will be equal to 3. So you can form any graphs which are complement to the cycles, and that will give you the answer. Now, what's the proof of this result? The proof is very simple, so I'm going to present it to you. Okay, so for a unit spherical, we know the EDM is spherical and has radius 1. Let S equal to 2W. So that's what I told you before. Then E transpose S is equal to 1. let B be the gram matrix satisfying BW equal to 0. So now I'm not putting the center of the origin at the centroid of the points. Okay? I'm not doing that. I'm doing it so that BW equals 0. In that case, this gram matrix satisfies this. It's very simple. Okay? So gram matrix satisfies this. Now, if you substitute for D the value that we are looking for, then B is equal to this. Therefore, to find delta, we need to satisfy these two equations. First, the gram matrix has to be positive semi-definite. So the gram matrix has to be positive semi-definite. Second, BW has to be equal to 0, which means W must be an eigenvector for A bar with eigenvalue 1 over delta. Okay? Now, the first equation implies that delta must be less than or equal to 1 over lambda 1 A bar. The second equation implies that delta must be greater than or equal to 1 over lambda 1 of A bar, so therefore must be equal. Okay, okay. And those are the references. So this is a recent book which covers the first part, and the other results appear in these papers. So any questions would be fine.
We have time for some questions before the break.
Professor, about the yielding entrance, is there a result about how the embedding dimension is changing with
Yes.
dependencies?
Yes. You can infer that from the theorems, yes.
Okay.
But I didn't talk about that, yes. Yeah, unfortunately, I didn't. This is really involved. And you can do the same for yielding also for spherical. So if you have a spherical EDM of radius 1, you want to know how far you can move a certain entry and still have a spherical EDM of radius 1. But that's much, much more difficult, and that's the part I skipped. Okay.
This is
Yeah.
in the second paper? Or
The yielding in the book, the two distance, the last problem is in the second paper, and for the spherical yielding is the third paper.
So can you fix the embedding dimension and ask if the yielding remains?
Yeah, you can answer that.
You can answer that?
Yes, because remember when I'm varying it,
Yeah.
there are two cases,
Yeah.
and in one case, if you move it a little bit, the dimension doesn't change. In the other case, it changes. It jumps.
Okay, so
It
that'd be
jumps.
interesting to see.
Yeah, I can talk about it. Yeah, you can do that. Yes.
So you have that the spherical EDMs are generic, essentially.
Yes.
So
Yes.
I guess the question arises, what kind of completion problems give rise to non-spherical EDMs? So that means essentially if you have an EDM completion problem, generically you're going to get a spherical EDM.
What? No.
That's a theorem?
No, depends. For a fixed n, if you fix n, then most of the matrices of the EDMs are going to be spherical because they're going to be in the interior. Because the embedding dimension is going to be n minus 1. So they are finally independent. If you solve, let's say, SDP, and if you have Slater condition, so you have a configuration where all the points are affine independent, you are going to get it. That's going to be in the on the face. Yeah, you're going to get that. Yes, but if there is no EDM with that embedding dimension, then you're going to get either spherical or non-spherical. I don't know.
So corollary would be generically,
If you
completion problems are, the optimal solution is spherical? Sounds like that. would be
well,
fair.
yeah. That's saying that if you have many completions and you use semi-definite, you're going to converge to the one with the highest embedding dimension. And if that embedding dimension is n minus 1, you're going to get that spherical. Yes?
I have a related question. So you said that the interior of the EDM cone is the spherical.
Spherical, yes.
And you also talked about these regular spherical
Yes.
EDMs where their centroid is
Yes.
centered at their centroid.
Yes.
What is the geometry of that set? Where
I-
does
I-
that
I-
set of regular EDMs?
I think there are some results, but I don't
Lie.
I don't recall them.
Is it a convex set?
Regular EDMs?
Yeah.
I have to think about it.
Yeah. Interesting.
Yeah, I have to think about
That's
it.
very interesting.
Yeah.
Any other question?
Yes.
What is the big complication with the radius being bigger than 1? What's happening there?
Okay. Okay, good question. So if you take the radius bigger than 1, it can go all the way to infinity, and then the set is not closed anymore.
Yes. All cones have that property, and if you all cones have that property, they go to infinity. So,
Yeah, it doesn't have nice. It's not nice to work with, and you can tell from the Cayley-Menger result. So the Cayley-Menger result only applies if you have radius less than 1. So for bigger than 1, it's not as nice as that case.
So I'm figuring, for example, optimizing over this cone of EDMs, okay?
Yeah.
And if you're optimizing, depending on constraints, you may be anywhere in the cone. And then if you have to limit yourself to radius less than or equal to 1, then
No.
maybe it's one more constraint in a sense.
Well, actually, the motivation for specifying that, my interest was in exactly radius equal to 1. Exactly radius equal to 1. That set is not convex.
Okay.
So you have the configuration is that you can have points here and point there, right?
All
But
right.
if you take less than or equal to 1, then that interval is convex. It's an interval. So it's convex. It's a sub-interval of the yielding interval. Okay? So that's why the results are nicer there. But the ultimate goal, my goal was radius 1. I want radius 1. But to get to radius 1, you have to relax the problem a little bit to allow for less than or equal to 1, and then you rule them out. That's the part I skipped. And if you want, we can talk about that. I can show you exactly.
Last question, too.
Okay, so this is really fascinating, and you know, it's related to combinatorial characterization of rigid graphs.
Yes.
And so I have to read through it and see if there's something there. But the matrix combinatorial characterization of rigid graphs that I've been looking at a little bit, and I think is very interesting, is Connolly's stress matrix.
Yes.
And I wondered if you looked into connections
Yes.
between what you've spoken about today and that matrix.
Yes.
Oh.
Actually, when I started looking at this problem, I started for yielding entries, how to characterize yielding entry. I started from universal rigidity. And I found the stress matrix.
Yeah.
Okay? But the stress matrix is going to tell you whether this entry is yielding or non-yielding. It's not going to tell you how far you can go or the upper bound, lower bound, right? But then when I found the explicit solution for that, the explicit form for the upper and the lower bound, and I thought, why use universal rigidity? It's an overkill, okay? So I can translate all these things to and present it in this way. And the rigidity matrix, I can form it explicitly to you, and it's going to be positive semi-definite with the highest rank, and it's going to be given in terms of the Gale transform. Okay, so it's the same, yeah. Except this one is better, which is surprising, that you can find explicitly the upper and lower bound.
Yeah.
Because you could solve an SDP, but this is a closed form solution, right? So then I decided to present it from this way. But the original work started from universal rigidity of the graph.
So what we'd like to do is we're given a distance matrix from some experiment,
Yeah.
and we'd like to know how to decide if it's globally rigid or
Yes.
in a given embedding dimension.
Yeah.
And so with the stress matrix, there's a procedure to do
Yes.
that. But the problem is you can't figure out where the minus ones and ones are because you don't have the solution.
Yes.
I'm looking for a pathway to do that from what you've described today. Have you thought in those terms?
As I told you, we know a lot about the universal rigidity, which is relaxation of the global rigidity.
Yeah.
So I can show you even how to get them in terms of, for simple cases,
Yeah.
how, in terms of Gale matrix. I can show you how to create the stress matrix.
The straight,
Yes,
is
I
there a
c-
combination? Yeah. Okay. Yeah, we should.
The universal rigidity is much easier than global rigidity. So the results in global rigidity, you require generic property, which Leo doesn't like. And many people don't like. But you have to. In global rigidity, you have no choice. In universal rigidity, you can get rid of it. You can only assume general position. And general position are very easy to characterize in terms of Gale transforms. And you can form actually the stress matrix. You can form it from two different ways. Okay.
So let's thank Abdo again.